foremost, I want to thank everybody for taking time from your busy schedules and joining us today. You know, the thing is, we want to basically share information on some of the things that we've learned and some of the methodology that we've kind of learned along the way over these past 4 years in testing and evaluating some of these FRs. So our goal here, basically the main takeaway here, is to show you some of our methodology, the capabilities that we have, along with the methodology that we're using to basically evaluate these FRs, and then go through some of the interpretation of the data into how we interpret the results to be able to better select or do the selection process in the for the FRs. So my name is Frank Zamora. I'm the Senior Vice President here over the Fluids Group. I've been with Premier since the beginning, which was June 1st of 2016. So again, this is our 4-year anniversary. The month of June we celebrated our 4-year anniversary since opening the Fluids Group. So again, thank you for all your support over these last 4 years. It's been a good run. Now we're going through some pretty challenging times. However, I think, you know, this too will pass. So along my 40 years of being in the business, we've seen a lot of ups and downs. So I think this too will come and go over time. So Brady, should we start?
Yeah, let's get started.
Okay. So
I guess real quick, just to mention, we have quite a few slides to go through. So Frank is probably going to answer questions at the end instead of trying to answer them all during the presentation, but please feel free to type your questions in as you think of them, and we'll try to address them all at the end. If we don't get to you, we will have those questions saved and we will send you your answers via email or a phone call after.
Absolutely. Absolutely. So again, we're the main goal here is evaluation and data interpretation of friction reducers. So our takeaways, as I mentioned earlier, are to understand the types of FRs that are on the market today and the functionalities, the application conditions and the performance properties that govern the FR selection, the laboratory methods for testing the FR and how we evaluate these FRs, and guidelines to compare the various FR performance and choose the optimum FR for that very specific application. So the outline again is to just basically review the types of FRs available, some of the structures. The one thing I do want to say is that we are not a manufacturer. We are an independent lab. So we really don't know a lot of the details that go in making and synthesizing these FRs. We are simply testing the FR for performance and determine specific properties. There's several types of FRs that come in various forms, and we've covered that. And then a lot of these, a lot of the functionality that we will go through to determining the type of FR that's needed for the specific application. And most importantly, what we want to cover here is the FR workflow based on the application. I think we have a nice little workflow that kind of help everybody to evaluate these FRs whenever we're either doing self-sourcing or wherever we're doing other types of evaluations of the FRs that are on the market today. So what is a friction reducer? Let's start from the very basics here. And Brady, before we start on what is an FR, one of the questions that I think is important is someone was asking if this was being recorded or not. Will it be available for those that were not able to attend?
That's correct. As after we finish the webinar, we'll email out the recording to everyone. And once it's approved, we'll put it on YouTube as well.
Okay, no, very good. So basically, it's a copolymerization product of the acrylamide monomer with other monomers. And we're going to kind of go a little bit through the building of the molecule, but it's very basic. It's a very high level. It's just to kind of give you an understanding of the basic premise behind a polyacrylamide or an FR. So an acrylamide is, the acrylamide monomer is neutrally charged. It's the neutrally charged monomer, So the resulting copolymer's charge is the dictated overall polymer charge. And I think that was an important point for people to understand. The synthesis condition, the degree of polymerization, and copolymer charge and structure dictate the final polymer characteristics, such as the molecular weight and the charge density. Now, the composition of this particular FR is going to ultimately determine the performance and application suitability, meaning that it's going to determine how salt tolerant this product may be, the stability, the viscosity and elasticity of this particular product, the compatibility with other chemicals. So I think it's important for us to understand the overall charge of the specific FR that we're going to use. And then the type of monomer, co-monomers that are being used is going to dictate a lot of what the overall price of the product is going to be. So here we have basically the polyacrylamide synthesis, the building of the molecule. And these are just examples of a few of the FRs that are available on the market today. What I basically wanted to do is just put out some of the basic ones that are out here. Again, we are not a manufacturer of these products, so we really don't know the secret formulations that go in polymerizing these things. But I just kind of want to give you a brief description of the actual polymer itself. So we start out with the acrylamide, and it's an amide because we have a carbon double bond oxygen bonded to a nitrogen. So by definition, it's an amide. Now this monomer is then polymerized with the acrylate monomer to form what is a polyacrylamide, the PAM. It's probably a very commonly used FR, so I kind of wanted to put that out there. And another one that's been used quite a bit is the copolymerization of the AMPs. And then we have two examples of other cationic polymers that are, or monomers that are available that will polymerize into a cationic FR. Again, I don't want to go into the chemistry. That's not what the goal is here, to jump into the weeds here, simply because we at Premier are not manufacturers and we really don't know the full polymerization process of this steel. The main thing that I wanted to make, the main point I wanted to make by that synthesis chart is that the acrylamide is a neutrally charged monomer, and that the polymer charge is dictated by the co-monomer. So again, I only had the cationic and anionic FRs. However, there are some neutral FRs as well, non-ionic FRs that are on the market as well. So these are just a few of the monomers that are available, and there are some others that can be polymerized to make a different form of FR. The other thing I wanted to make a point of in an example here, a good example of this, is that the polymers are a composition of repeat units, and these are the repeat units. And that number of repeat units is called the degree of polymerization. So I just kind of wanted to bring that up just to help you identify, whenever you're dealing with an FR, some of the characteristics involved. So the PAM, this base friction reducer, this anionic FR, which is copolymerized with the polyacrylate, is probably one of the most widely used FR on the market today, simply because it's a general purpose anionic FR, predominantly used in fresh water, light brines with mostly monovalent cations. So it's just more when the divalents are not present, more of the sodiums, the potassiums, very small amount of calcium. So moderate to high chlorides, compatible with anionic and non-ionic additives such as surfactants and scale inhibitors. So again, flow loop.
Hey, Frank, you went on mute on accident. You got to unmute.
How about that? Can you hear me?
Yeah, you're good now.
Okay. I had to move a screen over to the side, so I must have hit the mute button. Sorry about that. So I'll just kind of, I think I left off here on the compatibility with anionic and non-ionic additives, such as the surfactants and scale inhibitors. The flow loop compatibility evaluation is recommended when using cationic additives. And it's most important to understand that whenever we're dealing with clay stabilizers are positively charged. Therefore, whenever we add it to an anionic FR, it's important to determine whether this clay stabilizer that's being used, because there's a tremendous amount of various KCLSs, clay stabilizers. Some of them are, have a really strong positive charge. And that positive charge will affect the overall performance of the anionic FR, meaning that it probably will neutralize it, which means your friction pressures are going to be extremely high. Or it may create some form of incompatible goo downhole, which will not go away over time. As we mentioned, these are very sensitive to the divalents, such as calcium and magnesium. So these type of polymers are not recommended for a high level of divalent cations. AMS-based friction reducers, again, this is a somewhat of a new FR on the market for a divalent ion tolerant anionic FR. It is anionic in nature, but it is more tolerant to the divalent ion, like the calcium and magnesium. It also is more of a fit for purpose in non-ideal source waters whenever we're wanting to stay with an anionic FR. So it is modest iron tolerant to the Fe2 or Fe3. It is compatible with anionic and non-ionic additives, like we mentioned earlier, with the other anionic acrylate. And again, whenever we're using clay stabilizers, because it is an anionic FR, we recommend that we test for clay stabilizer FR compatibility. And what makes this chemistry a little more tolerant to these divalent ions is the AMP chemistry, which has a bulky side chain, which is circled here, and it is a strong anionic sulfonate group. And then whenever we're really looking for something that's robust in the cationic FR market, these are just two examples of monomers that have been polymerized with a acrylamide. The FR of choice when compatibility with other cationic fluid additives is needed, and it is used in most problematic waters when you have high divalent content and suitable for high TDS levels. Cationic FRs are also used in the acidizing world whenever we're trying to viscosify the acid or cross-link the acid, we use a cationic FR. So the types of friction reducers that are on the market right now. There's three basic forms that we deal with. One, of course, is the invert emulsion, the liquid emulsions or the inversion emulsions. This is the one type that's that was used from the very beginning. And then came the dry FR, which has been put into a slurry package, very similar to what you would put a war slurry into a slurry package, where you would have the solid suspended in an oil. And then we have the actual powdered version, which you can actually run dry on the fly or as a concentrate. Now, whenever you're trying to decide whether or determine, if you don't really know whether you're dealing with a slurry versus an emulsion, there is a texture to it. You can actually put it on your fingers and actually feel the texture, meaning that you're dealing with a solid material that is in a suspension form. So the liquid inversion emulsions, these are basically a polymer molecule that's packed inside a water phase droplet that is emulsified in an external oil phase. Mostly this external oil phase is a hydrotreated light distillate or an aliphatic hydrocarbon. And before the polymer can be used, the emulsion must undergo an inversion so that the polymer is released in the oil phase. And this requires the better this inversion occurs means the better surfactant package it has to release this polymer into the water to allow it to hydrate. So the surfactant package is important depending on the water that is being used. And of course, liquid emulsions form, in the liquid emulsion form, they facilitate better handling, transport, polymer loading, the way we measure. We are very good on location to measure liquids. So this is one way of actually being very accurate in measuring or delivering a inversion emulsion type of FR. And again, we're going to cover this a little bit more when we're doing testing and evaluating of various types of FRs. Of course, we're going to receive FRs that are in the inversion emulsion form, in the slurry form, and in the dry form. And in order to make them equal, we must understand, first and foremost, so very important, the actual amount of polymer that is present in the FR. So it's important for us to understand what is the percent of activity in the emulsion, for example. Let's start with the emulsions. We're given a specific gravity range between 1.06 and 1.08 in this particular case from the SDSs. So in order to come up with the amount of active polymer in this particular emulsion, we have to take we must know the specific gravity and typically what the percent of activity is in this particular product. So we take 1.06, for example, we take it by the weight of water. It's going to be a percentage by weight. So we'll have a specific gravity of 1.06, multiply that by 8.33 or 8.34, whatever people like to use for the weight of water. For the amount of material in 1 gallon per 1,000, we now have 8.83 pounds of actual weight density of the overall product. We take 28% of that and we come with 2.47 pounds of active polymer in this particular type of emulsion. So now we're going to basically, if we're trying to compare the emulsion versus the slurry, we now can then try to normalize the amount of active material in each one of the products. So as we mentioned, the liquid slurry FR, it's simply a dry powder that is a dry powdered FR that is dispersed in a null phase, and it's just in a suspension form. It's still the dry particulate, but it is in a liquid suspension. It's again in a hydrotreated light distillate or aliphatic hydrocarbon. Again, it could contain chemicals, it could contain surfactant packages or not. It could just be simply shear dependent, mechanical shear dependent on allowing this polymer to release from the oil and get fully hydrated. Again, because it is a liquid, it's easy to facilitate, transport, understand the polymer loading measurements. But what we do know is because it has more polymer loading per gallon of product, we're able to probably take less material to a location than what a 20% or a 28% would be, because you're going to have more activity on location simply because you've got more polymer there in the slurry itself. There's advantages and disadvantages to everything because it is a suspended slurry and it is a particle. It is particles that are suspended in either a organophilic clay or a block copolymer type thing to basically viscosify the mineral oil. Depending on that viscosity, these type of FRs may have a tendency to settle, versus an emulsion will not quite settle as fast. So in order to measure the amount of polymer loading required to do normalized testing, we have to know what the actual amount of dry material is per gallon absolute. So what it means is for every gallon, we will either have 3.5 to 4.5 pounds of active material in that 1 gallon of FR. That's an important number to know because whenever we come across and try to normalize these tests, we have 1 gallon of FR versus 1 gallon of slurry, 2.5 pounds of active material in this one particular gallon and 4 pounds of material in another FR. Whenever we do the normalization, we have to, if we were to run at 1 gallon per 1,000, that's only 2.5 pounds, which means in a 4 pound per gallon slurry, you would need 0.625 gallons per 1,000 of the slurry to come up with the same 2.5 pounds per gallon. And when we're doing the testing, it's important for us to understand that simply because 1 gallon of an emulsion and 1 gallon of a 4-pound slurry are not going to be equal, and the performance is going to be skewed. Whereas the dry powder is 100% active. Sorry, forgot to turn that off. But now you know the school I go to. That was the
That's pretty good, Frank.
Texas Aggie Warham. Thank you. So as I was mentioning, the dry powder is 100% active FR. The dry powder can be used as is, depending on the delivery mechanism that is on location to deliver the dry, or it can be used as a concentrate. You normally want to use somewhere between 2–2.5% by weight of water. Therefore, because it gets much higher than that in fresh water, it gets pretty viscous and almost unpumpable. As I mentioned, you do need a special dry add piece of equipment on location to actually measure and pump the dry material to the blender. In this particular case, in the dry, what controls a lot of the hydration rate is simply how fine or how coarse this FR may be. So the FR characteristics needed based on application. Basically, we need to understand what is it that we're trying to do on location. Are we just looking for friction pressure reduction? Are we looking for viscosity, for a wider fracture width so that we have more proppant transport? Or are we looking for proppant transport capabilities? So we have to understand early on, as we mentioned, a lot of the attributes and characteristics of FR, have to understand, whether we're dealing with high molecular weight FR, whether we have salinity, do we need a salt tolerant, how quick do we need it to solubilize, do we need viscoelastic behavior? All of these characteristics need to be taken into consideration when selecting an FR, because we have to base it on what is it that we're trying to achieve on location. So what is it used for? FRs, let's get the cationic system, for example, that can be used both in freshwater, saltwater, and acid systems. If we're wanting to use FRs in acids, you'd basically be using a cationic FR, whether you're doing just viscosifying or whether you're doing cross-link, you still need a cationic FR. But one of the primary purposes for the FR is simply for reducing the friction pressure on location. To reduce the friction pressure on location, we want it to work in most cases in fresh water, and in some cases in produced water, whenever we're now starting to come to the point to where a lot of operators are using fresh water commingled with brines. We want to be able to enhance the rate for the same amount of energy. We want to reduce the hydraulic horsepower demand when pumping, and we want to reach the maximum velocity to transport sand. So for example, if we have an FR that isn't functioning because for some reason, maybe the water quality may not be quite what we expected it to be, and we expect to treat or have a design at 85 barrels a minute, but we can only achieve 65 barrels a minute simply because of the pressure demands on location, then we have basically changed the frac design. We no longer are getting the velocity we need to transport sand. Therefore, we've altered the frac design. And by altering the frac design, we've now basically changed the production history or the rate in which we expect the oil to flow out of the well. So there's some things that change whenever we change the design, or whenever we can't get to the rates in which the design job was, or the rate in which the job was designed for, we then altered everything. So we also, FR basically pushes laminar behavior to the higher rates. That's how we get our friction reduction. And we protect our frac equipment. Frac equipment is very expensive, and it's important for us to make sure that we try to get as much of the erosion effect out of the system as we can. So we have something that is now come into the market, which is a high viscosity FR. These high viscosity FRs are a bigger molecule. They're ultra high molecular weights and greater than 10 million moles or grams per mole, which provides a high viscosity level. And these viscosities, like we mentioned earlier, could be simply for transporting higher proppant concentration on location or creating the frac width we need in order to be able to place that high proppant concentration into the fracture. These HVFRs also exhibit a viscoelastic behavior, which we'll get into a little later on, that promotes proppant transport capabilities. So the better you are in being able to exhibit this viscoelastic property, the further out we get this proppant into the fracture. We no longer have to worry about the settling effect at the immediate wellbore. We now have the capability to transport sand further out into the fracture. The efficiency in freshwater only. This is one of the downsides so far that we've seen with an HVFR, that the water has to be fairly fresh for it to function at its full viscoelastic behavior. And of course, viscoelasticity is a function of how these polymers interact with each other. And we'll go through that in a little bit in the viscoelastic testing part of the presentation. So here's the FR workflow based on the application. I really like this simply because it helps us understand what testing needs to be done. So we start off with the water analysis, and then we need to decide whether we're simply doing a slick water or more using the FR simply to reduce the friction pressure on location, or we're actually wanting frac sand suspension to transport high proppant concentration or get further proppant transport out into the fracture. From there, we then decide whether we want to determine the zeta potential, and I'll go through that here in a little bit. Evaluate it through the flow loop for the actual water, or we make synthetic water based on the actual water analysis whenever the water is not available to run these flow loops. And then we perform compatibility tests between the chemistry, between the FR and the chemicals that are going to be used. Whenever we're looking for an HVFR for proppant suspension application, we're going to use an we're going to measure the HVFR viscosity profiles at different shear rates. One, we want to calculate N and K. If we want to calculate the flow and consistency indices, we can then do that by doing the shear rate curve. We want to measure the HVFR viscoelastic behavior, and we use the oscillatory measurement to determine G prime and G double prime, and we'll go through that here in a little bit as well. And then we have a proppant transport model, a 3D model, which basically is a dynamic model used to quantify and visualize the FR elastic behavior. So we can actually see through this acrylic model how well, or the differences between one FR versus the other on how well it allows proppant to settle or not settle or suspend. So it's a very good visual to actually quantify and visualize the elastic behavior of the FR. And then we do our compatibility testing again to basically determine which chemicals are going to affect the FR and which ones are going to be the most compatible. Water analysis, we know that salinity affects the friction reducer. And the choice of friction reducer is going to be very dependent on the salinity levels. pH, FRs are very sensitive to pH as well. So we have to understand the elemental analysis. We were talking about monovalent versus divalent. So it's important for us to have the elemental analysis and TDS levels of that particular water to select the correct FR. As an example, we talked about the acrylate type FR, very sensitive to salt, therefore, and pH sensitive. So that wouldn't be a good choice for a high salt environment type of FR. Whereas an AMPS type FR, an AMPS-based FR is going to be more tolerant to that particular type of water, assuming we want to stay with the anionic FR. So again, because there's such a tremendous amount of use of water these days, it's important. These pits are collecting water from various wells. So it's important to know what the overall water elemental analysis is. You know, this is just an example where a few years ago, back in 2011, we were using 1.3 million gallons of water, where now we've grown to probably, this is a 2011, 2016, 12 million gallons or 13 million gallons, probably a lot higher than that in today's market. So we're using a tremendous amount of fresh water, but it's a compilation of various wells that are coming in to form these big old pits full of water. And then we're also using produced water to supplement that fresh water or allow us the opportunity to use some of this produced water to actually use it as a repurposing of that particular produced water back with our fresh water. So we use an 80-20, 85-15 or 70-30, whatever it may be, and blend of fresh water to produce water to actually use as the actual frac fluid. So again, it's important for us to understand what the elemental analysis is of these particular waters that we're using. And when we are using produced waters, it's important for us to also know what the iron content is or the iron level of that particular water. So again, as we mentioned, there's various reasons for the water analysis, and it's basically in our workflow. Step number one is analyze the fresh water. Let's understand what we're dealing with. It's the most important chemical that we're going to be pumping into the well. We need to know it to the design of the frac fluid. We need to determine the TDS levels, the elementals, whether we have more monovalent than divalent, what the pH is, the optimization of all the other additives as well. What's going to be the scaling tendency between this particular water that we're using and the downhole fluid that's actually in place? Are these compatible? Are we going to have any scaling issues? And we run scaling tendencies to determine that. Whether this water has been contaminated with any kind of spent acid. It's important for us to understand the pH. It's also important to understand the turbidity of the water. These suspended solids really do affect some of these FRs, and if the solids or the TSS is charged in some way. Remember, we're dealing with either an ionic, cationic, or a non-ionic type FR. So it's important for us to understand that turbidity, that TSS level. And then it's also nice to know what is it that we pumped in and what is it that we're flowing back. So to try to understand the differences between the formation fluid versus the water that was actually used for the frac. So here at Premier, we use ICP as well as an IC, the ICP to basically analyze the cations, the IC to measure the anions and alkalinity. So again, I mean, basically it's just an example. It's important for us when we're doing produced water to make sure that we understand the iron levels of that water that's being produced. It's also good to understand the amount of iron that is in the formation fluid. And the only way we're going to capture the formation fluid iron is to make sure that when we do the analysis or when we capture the sample, that we capture a sample that has been acidified, that we bring the pH down to about a 3 to make sure that the iron stays in solution. Otherwise, by the time it gets caught and by the time it arrives in the lab, that iron, that Fe2 that is in solution has turned to Fe3 and it's basically turned orange and it's all basically settled out. We're not going to be able to pick it up in the ICP. Therefore, we're not going to really get a true level of iron that is actually downhole. Sometimes we receive FRs and no one seems to know, or it's important for us to know what the charge really is of that particular FR. We have a methodology, we've developed a methodology in measuring zeta potential to determine that. So here we have 4 different FRs that, and then right now we're undergoing a research project to see what else will zeta potential tell us with regards to the overall performance. But for now, for the simplicity purposes, it is a very good way of determining whether you have an anionic, non-ionic, or cationic, and at what level of millivolts of zeta potential do you have? How strong is that charge going to be for that FR? We do this in DI water simply because there's other things and the elements in the water that also affect the overall zeta potential. Therefore, it's important for us. All we're trying to do is identify what the charge is in the FR. And so we use DI water to keep all the other components, all the other constituents out of the picture. And we measure the zeta potential to determine how strong of a charge it is, anionic or non-ionic, or again, we have two examples of two cationics, one mildly charged and one with a higher charge. I'm really excited about the zeta potential idea and the other things that zeta potential may be telling us down the road. So let's go into some of the methodology that we use. This is our friction flow loop. I think if there's anything that we take away from here is that the data that you get from this particular flow loop cannot be compared to data that you do in other flow loops. They are all going to be different simply because they're all manufactured differently. We have, in this particular case, we have a 3-pipe flow loop. We have a 3/8, ½ and 3/4 inch OD flow loop at 6 gallons a minute. We have the transducers separated at different intervals. Your or other flow loops may have those transducers further apart or closer. The thing is that it is all a relative measurement when you're dealing from flow loop to flow loop when comparing one product to another. So this particular flow loop is at 6 gallons a minute. It generates a Reynolds number in the 3/8 pipe of about 82,000, 83,000, and in the ½ pipe about 51,000. What we try to do here, and what's important, is to understand that this flow loop is only at 6 gallons a minute. It does not represent what you actually are going to see with respect to what's going on in a 4.5 or 5.5 inch casing string at 85 to 95 barrels a minute. The Reynolds number in that particular case could be up in the million plus. But what we want to do is we want to be able to compare the one FR to another. So what we want to do is we don't want to test it at the condition in which you're testing it or using it out in the field at a ½ or 1 gallon per thousand. It's too much polymer for this flow loop to actually measure or be able to evaluate one FR from another. So what we do is we stress out the polymer. By doing that is we minimize the amount of polymer that we're using in our system so that we can best compare product A to product B. Here's what the data generates. This is the raw data. If you see the red, orange, and yellow line, those are the actual baseline pressure readings of the transducers for water. And then once the FR is injected, we then see how well it hydrates, and then we have a drop in pressure, and that is what we measure, the drop in pressure, whenever we do the calculation. So that at the end of the day, when we evaluate these, we take these differential pressures and we come up with a graph like this, where we're measuring the point of injection, how fast the actual FR hydrated. This determines how quickly that polymer came out of solution or came out of the oil. The maximum amount of friction reduction that we saw in this case, 80%. Again, like I said, 80% in this flow loop may not be 80% in a different flow loop. Everything is relative. So product to product will be comparing under the same conditions. We're able to, at that point, compare product A to product B. How well does it maintain that friction reduction curve in the 3/8? In this particular case, we have a very good amount of friction reduction. It's very stable for the duration of the test. Again, with regards to the application, we're dealing with how long does it actually get to pump from the wellhead to the end of the perforation. We're looking for friction reduction. We're looking for 4 to 5 minutes. Some people like to see a little more than that, 10, 15 minutes. Simply they want to see the degradation curve as a polymer is sheared over time. Here's an example of the sensitivity of the FR with salinity. You see that In the 3/8, we have a very good friction reduction characteristic, but then again, we start seeing where some of these particular products will not quite function as well due to the salinity. And I'm going to have to accelerate here because I'm 45 minutes into this and I still got a little ways to go. Again, in the 1/2 inch, the main thing I want to make here in the 1/2 inch is that we're seeing more degradation in one curve versus the other. That is another characteristic that we look at when comparing the 3/8 to the 1/2 inch is, do we see degradation in the 1/2 inch after it goes to the 3/8? Here's a particular case, again, very good in the 3/8, but then we start seeing separation due to shear effects. The main point I want to make here is when we're evaluating this is that you can see a very slow hydration portion here in the blue line. That really doesn't really concern me just yet, simply because the polymer continued to give me friction reduction characteristics further down the road. That means that it wasn't quite, it was two things that could have happened here. One, I may not have had the right surfactant package to allow this fluid to come out, or I may not have had enough shear in my flow loop to help it come out. But in the field, these two products, product blue or the product 2 may work better than product 1 simply because I do have the amount of shear on location to help that polymer to come out and hydrate. The main thing that I want to see here is I have good stability in friction reduction characteristic. And you can see here that product FR2 still maintained a better friction reduction characteristic in the 1/2 inch, which means it had better shear resistance. The effects, we talked about earlier about the effects of a monovalent versus a divalent. In this particular case, what I want to show here is an AMPS versus a acrylate type product where we're dealing with a monovalent, a sodium chloride versus a divalent, which is a calcium chloride fluid. And you can see here that very quickly in the acrylate, the divalence at 5,000 TDS affects the acrylate. Whereas in my AMPS anionic system, it didn't quite have that same effect in the monovalent or in the divalent. Taking it up to higher, or this is again in the 1/2 inch. In the 1/2 inch, again, we see the same basic concept with regards to shear. So the 60,000, again, this is the 60,000. I have a mislabel here, but this is 60,000. This is not the 5,000 that is the way it's labeled here. So my error, my fault. So in this particular case, again, we see where the divalent are definitely affecting the actual monomers, but it doesn't quite affect it as much in the AMPS. So let's talk about rheology a little bit. So again, we're dealing with trying to understand rheology. Rheology is therefore trying to understand it, especially in an HVFR, is that we want something, FRs are going to be shear thinning. So we basically measure the HVFR in a shear rate pattern in order to be able to calculate N prime K prime for those that want to model N and K in their particular frac modeling. So we calculate the flow index, and that's the fluid deviation from the Newtonian behavior, and the K prime, which is the consistency index, is the average performance of the fluid over time. So again, Newtonian fluids generate the same viscosity value with certain shear rates. So N is 1. In an HVFR, shear thinning polymers that deviate from the Newtonian behavior, generating a higher viscosity level at lower shear rate regimes, N prime is less than 1. So again, the higher the value of K over time, the better performance of the fluid. What I want to emphasize here is that HVFRs are shear thinning. So here at Premier, we use a oscillatory rheometer, the Antimpar. We have there's several of them out there. We have the MCR 102. It performs as a rotation as well as an oscillation rheometer. And so for us to basically calculate N and K, we basically plotted on a log-log scale on a shear stress versus shear rate. And by taking the power law equation, we then can take tau equals K gamma to the nth prime power. Again, the trend line will give you this equation so that simplify it is shear stress is equal to K prime times shear rate to the nth prime power, where we then can conclude that we have a slope, we have the y-intercept, we have the r square. The r square simply is how well the points fit within that curve. N prime would be on the equation 0.6717. And then the 0.3348 is the K prime in dynes per centimeter squared. So that is converted back into pounds per square foot. And now we have N and K. So here's an example of an HVFR in a 280 K TDS fluid at room temperature. You can see the shear thinning effect, but you can also see the effects on an HVFR where it had basically it had no performance whatsoever in this particular high TDS. As I mentioned earlier about freshwater effects or the HVFR efficiency in freshwater versus brine, most waters have a TDS level of something. For example, Houston tap water, 500 TDS. You'll go down to the Brazos River, Navasota River, some of these other rivers, and TDS levels are going to be really, really low. You go over into some of these collection ponds or some of these rivers, and some of these rivers, for example, the North Canadian River, for example, up in Oklahoma, it'll have a TDS level of 4,500, which means that it is freshwater. However, it does have a high TDS level. Even at levels of 4,500, it has a tendency to affect some of these HVFRs. Here's an example where we have a 20-pound gel. You can see that the shear rate viscosity of a 20-pound gel is fairly decent. However, whenever we use an HVFR, in this particular case, or these particular HVFRs, we were not able to achieve that high viscosity in the low shear regime end of the shear rate. Which brings us to elasticity. Viscosity is one thing, elasticity is something different. So we use the oscillatory rheometer to establish, it's a well-established technique to quantify the viscoelastic behavior of the various fluids. So the main thing to take away here is that G prime is the storage modulus and G double prime is the loss modulus. And these are, in order to study the elastic behavior, there's two tests that can be performed here. One is the strain sweep, which is the shear strain amplitude sweep. This is where you run the sweep of strain in percent, keeping the angular frequency constant. That's one method. Method two is to have the stress sweep, the shear stress amplitude sweep, and this is the one that POFG uses, is to run the sweep at use a sweep of angular frequency, keeping the strain constant at a value, the amplitude at a constant, within the linear viscoelastic range, usually 10%. So that we end up generating, well, first let me, the description here. So whenever G prime or G double prime is greater than G prime, you end up with a viscous behavior. So let's go to the graph here. In ideal elastic behavior, G prime completely dominates G double prime, meaning G prime is going to be greater than G double prime. When G prime is equal to G double prime, meaning viscous and elastic behavior are exactly in balance. In an ideal viscous behavior, G double prime completely dominates G prime. So whenever we have G, in simplicity terms, G prime greater than G double prime, we're going to be in somewhat of a viscoelastic behavior. Whenever G double prime is greater than G prime, we're going to be more in a viscous behavior. So the dark lines are my G prime, my dotted lines are G double prime. So you can see that FR2 at 4 gallons per thousand had very good G double prime dominates G prime dominates G double prime. So I now have viscoelasticity. My purple line, FR1, has no viscoelastic behavior. Whereas Gore, which is always a nice example to have Gore, we have a 20-pound Gore of a 40-45 Gore system. We have G double prime greater than G prime. Again, viscosity, no elasticity. So here's the 3D model that we use to basically, it's an acrylic model. It's about a 1 foot by 2 foot, and then it has these fracture wings to simulate how well Proppant and visualize how well Proppant, the difference between viscosity and elasticity. So here is a Gore, a 15-pound Gore. It had a viscosity anywhere between 10, 11 centipoise. So we're looking at this model from 2 different angles. We're looking at it from the front angle, and then we're looking at it from the rear angle. So you can see Proppant, and this is a 4070 sand at 2 pounds per gallon. The rate is 2 gallons per minute. You can see very quickly how sand is actually settling because it has viscosity, but it has no elasticity. It has no Proppant transport capability. Very quickly, you can see that it's all basically settling out, not very far from the fracture. So whenever we have, whenever we do these, again, as I was saying, as we change, because we don't have the right FR, we can't quite get to the rate we need, or we have problems in the field, we're not going to quite meet the frac design criteria because we didn't achieve the actual velocity rate we needed to get Proppant transported further out into the fracture. Here, in this case, we have an HVFR, 11.6 centipoise, very similar in viscosity. We're going to see better elastic behavior. We're going to see the Proppant transport further out, carried out of the model. And that's why I like this particular 3D model, simply because it's a very nice visual to determine the difference between viscosity and elasticity. I'm almost done. Compatibility tests using the viscosity profile. So again, whenever we're trying to compare compatibility testing, what we basically do here is we draw a baseline across shear rate viscosity, and then we start adding the additives to determine which additive may have a detrimental effect to the FR. If that's the case, then what we do, we'll see a difference here. But in this particular case, we had no chemical incompatibility. Everything was very close within the margin. The effects of iron on FR, and I kind of want to very quickly throw this out here simply because we've done a lot of testing with regards to polyacrylamides and Fe3. What is their compatibility or incompatibility? So in a way, a test methodology is we do a test line, a baseline, no FR in the first example, and we add 50 parts per million of Fe3. We add 1 gallon per thousand of FR and add the Fe3, and you can see that the materials agglomerate. You can see the FR, the polyacrylamide, actually coming together with the Fe3, very reactive to the anionic and the Fe3 plus. So we end up with an agglomerated cloud of iron and polyacrylamide. And then in this particular case, we have one that disperses the iron very nicely at 1 GPT of FR with the same 50 parts per million of Fe3, and we end up with a very good dispersion of the iron. We don't have any agglomerating or losing the effectiveness of that polyacrylamide. We also measure the viscosities of these, so we also determine how much viscosity or how little viscosity we actually have at the end of mixing these two together. Again, the guidelines for evaluating the FR. Let's understand what the polymer is, what the loading is of each one of the polyacrylamides or which one of the FRs, so that we can evaluate these on a one-for-one basis, on an equal footing basis, and be fair to whoever it is that's actually providing the FR. A lot of this is also going to be performance related as well as economics. We don't deal with the economics part of the equation, so we don't know what it is that people pay for the FRs. That is, all we do is provide the performance criteria, and then it is up to the operator or the end user to determine what is the economic benefit of having this particular performance versus another. I can't emphasize enough a complete water analysis to determine the elemental composition of the water, the friction flow loop testing, understand the viscosity profile. I mean, these are the basics, understanding the elastic behavior of the FR, and determine and perform compatibility with the entire chemical package. Again, it's just simply putting the science ahead and after every job to evaluate the FRs to better enhance well performance and reduce the overall cost. Again, I apologize for going an hour. I knew it was going to be a lot of information, but I had everybody together. I wanted to present everything it is that I could possibly present at a very high level, because I think this is so important in evaluating these FRs that I would rather take the hour to give the information, and I will be more than happy afterwards to go ahead and we will take each and one of your questions and give you back your answer on so that you get full benefit out of the webinar. I cannot thank everybody enough for the opportunity for you to present to you, for you taking the time to listen to this our presentation. So again, I thank you for that. We are in some challenging times, but like I say, I know that this too will pass again. So if anyone has any questions, please send them to me. I'll be more than happy to answer each and every one of them. Again,